classical mechanics. This is kind of a review problem, but what I want to do is to take one situation and solve it 3 ways. So I'm going to solve it with Newtonian mechanics, and then I'll do Lagrangian mechanics, and then Hamiltonian mechanics. 3 ways. And the problem I picked is this right here. It's a mass on a string hanging down vertically. We call that a pendulum. So let's just do it. Let's just get into this, solve this 3 ways. We can talk about what works well, what doesn't work well, why you would use that. It's going to be fun. And I'm going to start with Newtonian mechanics. So in Newtonian mechanics, we have the following. It basically looks like this. It says the net force is mass times acceleration. And if I can find all those forces, I can find the acceleration. And since acceleration is the second derivative of position, I can find the position. That's the goal. That's the idea. Okay. So here, in this case, there's only 2 forces acting on the mass. There's the gravitational force pulling down, mg, and then there's a tension pulling that way in the direction of the string. Strings only pull. Now, this is a pretty tough problem because even though it's in most introductory physics textbooks, it's still pretty tough. Okay, the problem is that I have an expression for the gravitational force, but there's no expression for the tension. The tension is a force that's applied to the mass that makes it stay a distance r away from that point. So it just says, I'm going to do whatever I need to do to keep that mass at that, well, not getting further away. You can get closer. And so it's going to do whatever it needs to do unless it breaks. So it's a force of constraint. There is no equation for it. Yes, you could use some trick with energy to get that, but it's not trivial. I'm going to do the sensible thing and to switch coordinate system. So in Cartesian coordinate system, the tension changes magnitude and direction. But if I switch to a polar coordinate system, at least that tension won't change directions. So here's my polar coordinate system. I have the r hat direction in the direction of increasing r, and then this is theta hat direction, the direction of increasing theta. So that's my polar coordinates. And we're going to use that again later. But now I have F net r is mass times acceleration in the r direction. F net theta is mass times acceleration in the theta direction. So let's just go ahead and write down an expression for the net force in the r direction. So what do I have? Well, I have this gravitational force, and this is my r direction. This is the angle theta, right, because it's the same as that angle right there. So that right there is my component in the r direction. And it's the adjacent side of this right triangle, so it's going to be equal to mg cosine theta. And then the tension is in the negative r direction. That's a theta. Like that. In the theta hat direction, the nice thing is, like we said, the tension doesn't push in the theta hat direction, only in the r. So the only component in the theta hat direction is this part right here, which is mg sine theta, because it's the opposite side. But it's negative, right? Because theta hat's that way. This is in the negative direction. So it's negative mg sine theta. Now, what can I say about the acceleration in the r direction? And that's one that can be tricky, right? Because you can say, well, look, the mass doesn't change its position in the r direction, so the r acceleration is 0. But that's not true, okay? That's not true because the r coordinate has a 0 acceleration, but there is an acceleration in the r direction. So I'm going to post a link down below deriving the polar acceleration in polar coordinates. But the key is that if I have, here's the short version. If I write r as r hat, so this is my vector position, that's my polar coordinate, and that's the unit vector r hat. If I take the derivative of this, if I'd say, let's just call it v, that's going to be r dot r hat plus r dr hat dt. So r hat is not constant. That's what makes it so not great compared to Cartesian coordinates, is that when this moves, r hat changes direction. So that's not 0. And when you do it again, you get the following. So here in the r hat direction, I get mass r double dot minus r theta dot squared. That's the r hat acceleration. And then in the theta hat direction, I get theta double dot plus 2r dot theta dot. That's right. I always forget that. That's right. Okay. So r double dot's the second derivative of the r coordinate with respect to time. R dot is the first derivative of r with respect to time, the coordinate. Okay. Now you can see here that I don't really even care about this motion, right? It's not 0, but it has a t in there, and I don't really want that. This equation down here does not have a t in there, and it has r. So here I can say r is equal to r. It's constant. So that means that r dot is equal to 0. This equation now becomes negative mg sine theta is going to be theta double dot. Oh, mass. I forgot the mass. M theta double dot. Oh, I messed up. This is I was looking at my units. This is r. So this is r. Sorry about that. I'm not fixing it. Okay, mistakes are just part of doing stuff. It's okay. But see, I caught it. You know, how did I catch that? Because I was looking at the units here, and it doesn't have units of acceleration. Theta double dots, radians per second squared, and that's kilograms. And I need a distance unit in there, and I remembered there is an r there. So, good job. Okay, that's it. I can now solve for an expression for theta double dot. The mass cancels. Theta double dot is negative g over r sine theta, and we're done technically. We're gonna do more. Okay. So there's two ways you could solve this problem. Number one is to say if theta is small, then sine theta is approximately equal to theta. So this equation becomes theta double dot negative g over r theta. And this is simple harmonic motion. Okay. Now, if you want to deal with large angles, now we have a problem. So for large angles, I'm gonna solve this numerically, and I'm gonna do it in Python. So let's say delta t is 0.01. So during that time interval, I can assume theta double dot's constant. So I can calculate theta double dot with this equation, and then I can say theta double dot is delta theta dot delta t, which is theta 2 dot minus theta 1 dot over delta t. So theta 2 dot is theta 1 dot plus theta double dot delta t. The dots mean derivative with respect to time. Did I say that earlier? Okay, if you were like, hey, what's this dot stuff? It's not an umlaut, okay? It's a second derivative with respect to time. So I calculate theta double dot. I know the theta dot to begin with, and I can solve for the theta dot at the end. And then I can do the same thing with theta dot. Theta dot is delta theta delta t, theta 2 minus theta 1 over delta t. So theta 2, theta 1, theta dot delta t. Then I just go back over here. So I do this first, and then I update theta dot, and then I update theta, and I do the whole thing over again. Now, I need my initial theta. I need my initial theta dot. I need my g. I need my r, right? Because then those are constants. So let's do that in Python, and let's just see what it looks like. I'll just plot it. Very simple, very quick, and then we'll go on to the next method, Lagrangian. But you see here, if I switch to polar coordinates, it's not too bad, but then you have to know the acceleration of polar coordinates. That's the problem. Okay. Python time. Okay, so let's do this in Python. Let's make a graph. G1 is graph. I'm going to plot theta as a function of time. So let's say title equals pendulum. So, there was some discussion online about, should you use WebVPython, should you use Jupyter Notebooks. I mean, for me, it's all about, like, how do you do this stuff? What does it mean? Not what's the quickest and best way. It's all about understanding. If you understand a numerical calculation, you can do more complicated things later. Okay, so x title equals time. Y title is theta, and then width, spell it right, 400, height, 200. And then F1 equals G curve, color equals color dot blue. Let's just make this as simple as possible. So t is 0, dt is 0.01. Theta, let's start theta out at 45 degrees. So it's 45 times pi over 180. I'm converting to radians. Theta dot is my initial velocity. Let's say that starts from 0. And then r, if I had a pendulum, it'd be 0.2 meters. So I'm just going to put 0.2. And then g is 9.8. So I've already included g in the direction, the y-hat direction, so don't put negative g. While t is less than 5, I'm just picking a value. So I'm going to calculate theta double dot. Theta double dot, I call it d dot, double dot, is negative g times sine theta divided by r. Now I'm going to update theta dot plus theta double dot times dt, which I just calculated. Now I'm going to update theta. Theta equals theta plus theta dot times dt. Now I'm going to plot it. F1 dot plot t theta. And now I'm going to update my time. T equals t plus dt, because I got to move to the next step. Let's run it. There you go. And that's what we'd expect. I mean, we're expecting it to look like a simple harmonic oscillator. This isn't, because I had a large angle, but you get the idea. So it worked. The end. Okay. Let's go back to the board and do the same problem with Lagrangian mechanics. I mean, I'd love to have all these solutions on the same board, but this is not going to fit. So hopefully you got all that. Let's just jump right to Lagrangian. I'm going to erase this stuff just because I want to make it look a little bit cleaner. So Lagrangian mechanics, here's the very short version of Lagrangian mechanics. It says that the Lagrangian is the kinetic energy minus the potential energy. And the cool thing here is that we can use whatever coordinate system we want. We can make up any generalized coordinates. And if we have generalized coordinates q, let's just say it's one dimension, then I get, what we're doing is we're minimizing the action integral. And the path that minimizes the action integral is the path of the actual motion in Lagrangian space. I can't remember what it's called. Okay. But to do that, we use the Euler-Lagrange equations, which says that the partial of L with respect to q, where that's one of my generalized coordinates, minus the time derivative of the partial of L with respect to q dot, that's my generalized velocity, is equal to 0. And so what's great about this is that I can pick whatever coordinate system I want to describe the system. So if I have this moving back and forth, and the only thing that's changing is theta, I can say, well, my variable is theta. That's the only one I want to worry about is theta. So I can use this and change the q's to thetas, and I should be done as long as I get the kinetic energy in terms of theta and theta dot, and the potential in terms of theta and theta dot. Of course, we have kind of a problem there. How do you write the kinetic energy with the coordinate theta? So we'll get to that. But let's just say if it was in Cartesian coordinates, I would write the kinetic energy as 1/2 m x dot squared plus y dot squared. And then I would write the potential as mgy. Well, for both of those, what I'm going to do is to get my generalized coordinates in terms of x and y, or y and x in terms of my generalized coordinates. So if that's my angle theta, then my x value is going to be equal to r sine theta, right? Because if this is x, then that's the constant r, that's the adjacent side, so it's r sine theta. Y is going to be negative r cosine theta, because here it's that distance right there, but it's in the negative direction if I'm calling that my origin. So that's that. So that's going to be useful for my u, but now for the kinetic energy, I need to get x dot squared and y dot squared. So let's take the derivatives. X dot is going to be, and it's a little bit nicer because r is a constant. So I get r theta dot cosine theta. Remember, if I take the derivative of sine theta, I get cosine theta, but then I have to take the derivative of the inside. So I have to take the derivative of theta, which is theta dot. So that's how I get that. And then y dot is going to be equal to r theta dot sine theta. So here, the derivative of cosine theta is negative sine, so that cancels that. And then I have to take the derivative of theta, so I get a theta dot. Now when I square these and add them together, x dot squared plus y dot squared is equal to r squared theta dot squared cosine squared theta plus r squared theta dot squared sine squared theta. I can factor out an r squared theta dot squared, and then I have cosine squared theta plus sine squared theta. So that's just 1. So I get r squared theta dot squared. So that's not too bad. So now I can write the kinetic energy T is 1/2 m r squared theta dot squared. U is negative mg r cosine theta. Now I can write my Lagrangian. So you kind of have to do that with Lagrangian mechanics. You have to do some type of work to get the Lagrangian, but once you do, it's not so bad. So here, L is going to be 1/2 m r squared theta dot squared minus the potential, but the potential has a negative, so it's plus mg r cosine theta. Now I can apply the Euler-Lagrange equation to get an equation of motion. So let's just do this in pieces. I'm going to take the partial of L with respect to theta. Remember, Q is just a generalized placeholder coordinate. I'm actually using theta. So down here, if I take the partial, it's a partial derivative of L with respect to theta. There's only one term, it's right here, and so I just get negative sine theta. And I don't get theta dot because it's a partial with respect to theta, not T. So this is going to be negative mg r sine theta. Now let's do this part right here. I'm going to say the partial of L with respect to theta dot. So there's only one theta dot, and it's right here. So if I take the partial of that, I get the 2 to come down. I get 2 over 2. I get m r squared theta dot. Now I need to take the time derivative of both sides, which is pretty easy because the only thing that depends on time here is theta dot. So the derivative of theta dot with respect to time is theta double dot. Now I can put it all together. So I have this negative mg r sine theta minus m r squared theta double dot is equal to 0. And I can move it to the side, the m's cancel, and I get r squared theta double dot is equal to g r sine theta. I'm going to divide both sides by r squared, and oh, there's a negative. That's not negative. Theta double dot is negative g over r sine theta. And that's exactly the same thing that we got before, right, with Newtonian mechanics. The only advantage here is that I don't even have any tension force in there to even try to get rid of. It never showed up, right? Because in the Lagrangian, in your generalized coordinates, you can pick some strange system of coordinates that just agrees with your constraints. So if I have a constrained system, no friction, right? If there's friction, then this doesn't work because you can't write the potential energy and it just doesn't work. There's a way to make it work, but you don't want to do that. So I can let it all move along, and there you go. Cool. Okay, so that's Lagrangian mechanics. If you have constrained systems and you have forces that you don't know, forces of constraint, Lagrangian is almost always better. Okay. Now let's do, that was 2. Let's do the Lagrangian, the Hamiltonian way. I'm going to keep my Lagrangian right there. Okay. So in classical mechanics, if you learn how to do Lagrangian mechanics and then you do Hamiltonian, you're like, wait, we just did that. That just doesn't really matter. Yeah, that's going to seem that way, but then I'll talk about why we need to do that. So what we're going to do is to first write the Hamiltonian. So the Hamiltonian in generalized coordinates is P Q dot minus L. And then we call that the Hamiltonian, where P is the generalized momentum, Q dot is the generalized velocity, and L is the Lagrangian. So now we need to find the momentum. And you can say, oh, it's mass times velocity, but you can see here that we don't really have that because we don't have our coordinates theta. Theta dot times mass is not the momentum, right? So we need to find the momentum. We can find the momentum in general. P is the partial of h with respect to q, right? Okay, let's just go ahead and find the momentum. So that's going to be equal to the partial. Oh no, I need to find the partial of L. Partial of L with respect to q. So the partial of L with respect to theta in this case. So if I go through here, no, theta dot. It's theta dot, right? Partial of L with respect to q. It's theta dot. I'm almost positive it's theta dot. Yeah. I'm pretty sure. If I make a mistake, I'm going to go back. But just note, I'm at a decision point here. Okay. So the partial of L with respect to theta dot is going to be m r squared theta dot. Right? Because it's just theta dot squared. And that's going to cancel. So now I can put it all together. So h is going to be equal to p m r squared theta dot times theta dot, which is theta dot, minus L. So it's going to be minus 1/2 m r squared theta dot squared. And then I have minus this. So I get minus m g r cosine theta. Now you can see here that I get some cancellations. Here I have an mr squared theta dot squared minus 1/2 mr squared theta dot squared. So that's kind of nice. Yeah, so this is going to be equal to 1/2 m r squared theta dot squared. That's that plus that minus m g r cosine theta. Now we're not done, but you can see here that this is the same as my Lagrangian, except my Lagrangian was 1/2 m r squared theta dot squared plus this, and here we have minus. So we actually get the total energy. So in most cases, the Hamiltonian would be the energy. Okay, not always. Okay. Now I want to get the Hamiltonian in terms of p's and q's. So I need to get this. I got theta, but I need to get this in terms of p. So p is mr squared theta dot. So I mean, there's a couple ways you could do this. I could just solve that for theta dot. Theta dot is going to be equal to p over mr squared. So theta dot squared is p squared over m squared r to the 4th. And when I substitute that in, I get h is 1/2 m r squared p squared m squared r to the 4th minus m g r cosine theta. And so here I get that cancels with one of those, that cancels with that, and so I get h is p squared over 2m r squared minus m g r cosine theta. So that's my Hamiltonian right there. Okay. Whew. And like I said, I told you were going to say this is crazy. And, kind of it is. I get it. Okay. So now we have a Hamiltonian in terms of p and theta, p and q, and we can use the following Hamiltonian equations. Theta dot is the partial of h with respect to p, and p dot is negative the partial of h with respect to theta. So we have two equations. So let's do this first one. Theta dot is going to be the partial of h with respect to p. If I take the partial of this with respect to p, I only have one thing in here, and it's this p, so I get p over mr squared. P over mr squared. And that's theta dot. And then if I take the partial of h with respect to theta, I only have this term right here. I get mgr cosine theta. Take the derivative, I get negative sine theta. I had a negative there, and then I have a negative there. So I get p dot is negative mgr sine theta. And we're actually done, and I'm going to model this, but I want to show you that this is the same solution that we had before. Because the key thing here in the Hamiltonian mechanics, remember my other solution, theta double dot, is negative g over r. sine theta. That's what we had before. That's a second order differential equation. Here I have two first order differential equations, and that's the big difference with the Hamiltonian, is that you get two first order differential equations, which I will solve numerically for you. Okay, but to show you that it's the same thing, I'm going to take the derivative of both sides of this. So I get theta double dot is equal to p dot over m r squared. Now p dot is that, so I get negative mg r sine theta over m r squared. Mass cancels, that cancels. Negative g over r sine theta. So I get the same equation, okay? But what we're going to do now is to use these two equations. I want to show you how to solve this numerically. So what I'm going to do is to, again, break this into short time intervals, and I'm going to calculate p dot. So let's do that. So p dot with that, and that's going to be equal to delta p over delta t, or p2 minus p1 over delta t. So I can update p2. I can update p. p2 is p1 plus p dot delta t. And then, now that I've updated p appears in there, I'm going to calculate theta dot. So theta dot is delta t. So theta 2 is theta 1 plus theta dot delta t. And then I do it all over again. So let's just add this into our other program and see if we get the same thing. So I'll have two graphs, but we'll do that. Okay, so switching over to Python right here. No, this one. Okay. I'm going to make a second graph. F2 equals G curve, color equals color dot red. And then down here, let's just do it again. I'm going to just make a new graph. So t equals 0. I'm going to reset my t. Theta equals 45 times pi over 180. You'll notice here that I need initial theta and initial momentum now. So let's just, you can say the mass cancels, but I actually kind of need the mass. So let's say the mass is 0.1, and I'm going to write the initial momentum. I'm just going to give it a value. Okay, I'm going to say it's 0 though. So P1 P is equal to 0. Oh, P dot. No, P. Yeah. P, because I need that up there. P is equal to 0. So now we can make our loop while t less than 5. The first thing is to calculate P dot right there. So P dot is negative m times g times r times sine of theta. Now I'm going to update p. P equals P dot P plus P dot times dt. Now I'm going to calculate theta dot. Theta dot equals, no. Theta dot is equal to P over mr squared. P divided by m times r squared. And now I'm going to update theta. So now I can make my graph. So F2 dot plot t theta. Now I'm going to update time, and let's run it. And the two graphs are right on top of each other. Okay, they're right on top of each other. I do want to show you, though, one tiny mistake that you can make. It's not terrible, but this order of operations here does indeed matter. You want to do highest derivative terms first. So the highest derivative terms are momentum, update momentum dot, update momentum, then theta dot, update theta. And just see if I change this order, what if I said I'm going to update this first, I'm going to put this up here, and then I'm going to update momentum, then I'm going to update theta. Let's just see what happens. Order of operations matters. And you'll see that we get something that doesn't look right. It looks like the energy is increasing. So that's clearly not what's going to happen. Now, you could fix that by making a smaller time interval. So just go down here and put dt at 0.001. Of course, you're going to pay for that with more computation. And it fits better, but still not perfect. Okay, so you always want to do highest order derivatives first. So p dot p, theta dot theta, and then it'll get pretty good thing. And this would be also a good way to plot the phase space. And that's really, let's go back over here to wrap it up on the overhead. This method, since you're dealing with theta dot and p dot, it's actually good for plotting a phase space. And so in phase space, we have p versus theta. And so you get, you'd get some circular orbit like that. But the nice thing is if I have a whole bunch of particles, we can talk about volumes in phase space and stuff like that. So it can be more useful for systems of particles. But anyway, I think that's a good review of the 3 ways to do this problem, which is not the best problem anyway. Hope that was useful. And I will put that polar coordinate derivation down below later.